Hi everyone and welcome back. This is SANS Offensive Operations CTF. It was a 6-hour CTF or maybe an 8-hour CTF hosted yesterday. In the CTF I ended up getting first, which was pretty exciting. For this video I'm going to be covering every challenge. There were 2 challenges I didn't solve during the CTF. One because I'm dumb, and the second one I'm still not convinced was solvable. So if anyone did solve Hippity Hoppity, please let me know. But I'm pretty sure the remote binary was different. And with that, let's get started. The first 4 challenges are these JavaScript challenges. They're kind of JavaScript or JSWTF challenges. So it says, we heard you like JavaScript. We scrambled some nice JavaScript code for you to review the provided code snippet, and send the appropriate API request to get the flag. And we're given a website. So for all 4 of these challenges, we're going to be given a little snippet like this. And this is the remote endpoint. And basically we need to send a request to this with the correct payload. And if we do it correctly, we get the flag. And for all 4 of these challenges, there's just like a little JavaScript trick, I guess. For this first one, we can see we have to make a post request to API stages 1. It's going to take the password from our body, and then it's going to compare password to BAAA, and then return the flag. So we just need to send BAAA. But if we look closely, we can see that the trick for this challenge was it's not actually BAAA. There's 2 pluses here, which is very strange. Since this is JavaScript, we can just execute it and see what happens. So I'll open up the terminal. We'll go down here, make it a little bit bigger. Too big. We can see BA++AA is actually banana, and it's specifically this NaN is not a number. So you can see if you do plus A, you get not a number, and then it's being casted to a string because there's a string on both sides. So this was the trick of the challenge, is just realizing that there's 2 pluses there. So to solve it, we can just write a little script, import request, r equals request.post. We'll send a post request to that endpoint. The password is banana, and if we do that, we should get the flag. So Python 3, stage 1. And we get the flag, banana, 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 banana. The second one, let's go to next. It's just stage 2. So router post to API stage 2. This time it's going to take the password, and the password has to be equal to 0.1 plus 0.2. And if it's equal to 0.1 plus 0.2, which, you would think is 0.3, we get the flag. But if we try it, 0.1 plus 0.2, we can see it's actually 3.004. That's just because floating points, they're a little bit weird, and usually there's like a little bit of rounding on the side. So really we want to pass this and not 0.3. So we can do that. Stage 2. So we're going to make a post to the second stage in the password, and our value we're sending is 0.304. And we should get the flag. So Python 3, stage 2.py. There we go. IEEE 754 floating point with you. So for the third one, router.post stage 3, the secret is equal to this. There's some fun like JS obfuscation you can do with stuff like this. You can actually build out strings. We could try to figure it out, or we could just send it to the JavaScript console. If we do that, we can see the password is octocat. So we just need to send octocat to the endpoint. Again, same sort of solve script, stage 3. Password octocat, print out the flag, Python 3, stage 3.py. And we get the flag. Weird JavaScript moment. So fun. And for the last one, stage 4, we're going to send a post request. This is going to have the days parameter instead of password. It's going to make sure that days is a number. Then it's going to parse the int that days, mod it by 7, take the absolute value, and then the day of the week is from 0 to 6. If it's not between 0 and 6, the day is payday, and if the day is payday, we get the flag. So somehow we need to pass a number that passes type of equals number, and when we parse it, mod it by 7, and take the absolute value, it's still not between 0 and 6. This seems pretty tricky. If it wasn't for this math.absolute value, maybe you could do like a -1 mod 7, and so this would not be in the range, but we have the absolute value. If it wasn't for this number check, there's a lot of different things we could pass in there, but that won't work. The trick was that you can just pass a very large number, and that eventually gets cast to infinity, I think. And so one way to do that is you can do 1e, so scientific notation, and if you just pass in like a very big number as a string, this, or just as an integer, this is a number, so it'll pass the number check. But when we do parse int on this, parse int on 1e10000, we get not a number, then modded. Let's do it up here. Mod 7 is still not a number. Absolute value of not a number is still not a number. So when we go through this switch case statement, it's not going to match any of those because it is a not a number. So we're going to get our payday. So like I said, the trick was just pass a very large number. To see what the solution looks like, we'll go to stage 4. And here we go. Same thing, post to the endpoint, content data. I was trying a bunch of different stuff. You can get rid of all this header JSON stuff, but the answer was days, and then I just passed in a very large number, and we should get the flag. Python 3, stage 4. Here we go. Too big to handle. So fun. The next 4 challenges are called badfish. For this challenge, we're given a badfish.image file. So if we take a look at it, we can see we have a DOS, master boot record, boot sector. Cool, so we can run binwalk on it. We could try running this in QEMU, which is one way to do it, but we can see if there's just any file systems in there. Oops. And maybe we can just mount that, which should be a little bit easier. And we can see here's a Linux ext file system. So we need to copy the offset, and then you Google for the command to mount one of these file systems, since I can never remember it, but here's the command I ended up using. So let's jump into a Linux system. So I'm using Docker for this. Let's make the directory temp, mount badfish, then we run it. So now we have the file system mounted locally at mount badfish. And so now that we're here, we can actually start the challenge. Like I said, there are 4 flags hidden somewhere in this file system. We just have to find it. This was kind of like a grep searching challenge. The first one was in Etsy app sources. If you go down to the bottom, you can see it here. One swim up the repo. So that was the first one. The second one was in home Nemo bash RC. We can see it all the way down here. 2 smelly cat. The third one was in ls bin. Somewhere in here. I guess it starts with a 3, so it would be up here. 3, strings are bad, so it's just the name of a binary, I guess. And then the last one was in the temp folder. Oops, the local temp folder. LSLA. There's a hidden folder called D. If you go to the cron tab for root, you'll actually find this being executed. So we can cat it out. It's just some Python script. So what we can do is just take this. Instead of evaling it, we're just going to print it. So we'll take this, run Python. We'll run it. Then we'll print out test. Test is going to execute some base64. So let's run this, see what it's decoding to. Oops. Why isn't it happy? There we go. And it looks like it's going to do some netcat port, but we can see the flag here. 4 sneaky. So the next set of challenges are in between the lines. For this first one, we're given a download gift. To solve this one, I used a tool called Stegosolve. It's a little Java applet. You can find it online. So we're going to open the file. It was called chow.gif, and we're given this little Nyan cat sort of thing. So we can go to Analyze and then Frame Browser. And if we just click through, eventually we'll see right here, it's a little dark, but there's the flag and it says flag split second view. So that was the first one. For the second one, it says, I hope you can read fast, and we're given littlebox.gif. So I think this was the same one. We're going to do open little box. Oh yeah, this one was a little bit annoying. Frame browser, it's the same thing, except it's 1 character per frame. I don't know if I can make it bigger, but you can see it says FLAG bracket, welcome to the little something. I think it was like 100, yeah, it's 100 characters, and basically I just went through frame by frame and copied it character by character. It said something about using like Tesseract, I think, or an OCR, but I think it's easier just to copy over the 100 characters. And then for the last one, it was a WAV file, so we can open it up in Audacity. File open, test wave. I like to view these as histograms. What is it? Test view? Spectrograms. Sorry, spectrogram, not a histogram. And you can see there's only 2 different notes. I don't know if I can scroll in. There we go. Well, too much. But you can see there's 2 different note types. There's like this high note and this little note. And basically, if there's only 2, you can kind of assume it's binary. So what I ended up doing was I played it and I just kind of viewed this, and in a notepad on the side I typed out zeros and ones, so it would go 0 1 1 0 0 1 1 0 0 1 1 0 1 1. I don't want to do it again, but if you do that, you'll get out some binary, and then you can take that binary and you can go to CyberChef, or any tool, but you type in the binary or all the zeros and ones up here. Oops. And then there's one of the operations is from binary. You just do this and you get out the flag. I forget what the flag said, but that was the challenge. The next set of challenges were called Taskus. These were 4 challenges and we're given a website. So if we go to the website, it's just called Taskus Pro. We can create an account. So we'll say SJP demo, SJP demo, SJP demo. We agree to the conditions. And we're ready. So SJP demo, SJP demo. Cool. All right. So now that we've logged in, we can create task. There's some user settings. The trick to the first challenge was if we look at the network request, we'll see that the way it grabs task is pretty interesting. It actually grabs it based off of the user ID. So a little hard to see, but let me copy this out. We can see from the URL, it's doing task, API task, and then 862, which is my user ID. So we can try grabbing like the first or second task. And if we look at the challenge description, it says, see if you can leak the flag hidden inside the admin account. So maybe we're supposed to leak the admin task. I created 2 accounts and I was able to see that I could leak tasks from a different account. So we know it's possible. We just need to find the admin ID. To do that, I wrote a little script all the way over here. Was it this one? Nope. Code. Task.py. So it's going to connect. It takes some cookies, and then it's just going to iterate through all the tasks, and maybe we'll be able to find the admin ID and leak their task. So we can go Python 3, task, and it's just going to start iterating through. I think the admin was like 63 or something like that. And there we go. We found the admin ID. So the admin ID is 64. And well, we don't know it's the admin yet, but there's a user with ID 64. And if we look, we can see we have the flag here. It says IDOR's insecure direct object reference in APIs for the win. There's 2 other notes. There's one that says move site directory from app to var www. So that could be interesting. And it says it's incomplete. And then there's another task that says disable task listing for admin. So cool. So this was the first flag. If we go to the second flag, it says we need to try to log in as admin. So now that we know the admin's user ID, there was another endpoint, which was the password, change password. So if we see here, we're allowed to change the passwords and we give it a user ID and a new password. So we could try to change the password for the admin. So we'll send it to repeater. And this is Burp Suite, by the way. And the admin ID was admin ID 64. So we'll say user ID 64, password 123456778. We submit it and it says, congrats, this would update the admin password, but because of broken access control, due to shared infra, here's the current admin password, broken pass control login. So we can take this password and let's log in as the admin. So admin, type in the password. Cool. And the flag is down here, flag broken access controls. Sweet. I think for the next one, it said something about files on disk or something. So if we play around, there's this new admin dashboard, and you can use it to import and export config. We can see specifically the exciting thing is this site logo. You find out if you export a file and then import that same file. It's just this config. It'll say something about like invalid PNG file, which is pretty interesting. And you can see there's a PNG file here. So you can see it's making a web request. So you can set up like a webhook site or an ngrok or something, and you'll see it's actually making that request. So we have something to play with. We at least have server-side request forgery. So let's take that request where we're importing the file. We'll send it to repeater, and we can play with it for a bit. So the site logo is the one that seemed interesting. So the first thing we can do is file etc password to see if we can load up files locally on disk, and we can. It even prints out the contents for us. So here's the etc password. Once we know that we have files, we can start enumerating the underlying host. An easy way to do that is to use the procfs. So you can do proc self command line. So procfs is just a thing on Linux systems where just gives you a bunch of like process debug information. So we're going to ask for the proc. Normally you would specify the process ID, but you can also say self, which means, my process ID, since we don't know the process ID. If you didn't know, you can also just guess. They start at 1 and they just go up. And then we're going to ask for the command line to see how this process was started. And we can see it was started with node app index.js. So we know where the file is. So let's go load it. App index.js. And cool, we get the source code. So normally you would take this out and you would put it through like a prettify or something so you can actually read the source code, but we're just gonna kind of skip that. We can see the first flag is right here, bless thy libcurl protocols. For the last one, it said there's like a secret route or something like that. We can see it's requiring routes, so we can try loading that. So it'd be app routes index.js. Again, you should take these contents out, put it into a text editor. It's just normal JavaScript code though. Eventually there's like some secret endpoint or something like that. If you look, it's requiring this thing called helpers debug helper. Somewhere down here, there's like secret endpoint or something, I forget. But we can load this debug helper. So helpers debug helper, all the way down, debug helper.js. Let's try to load this file. We can see when we load this debug helper, it's going to try executing opt debug info.bin. So we'll grab this file. Opt debug bin. Cool. This is going to download a elf file. We can see it starts with elf, the magic bytes. But if you go through, you should download it and open it up in Ghidra. But eventually you'll see something about like a flag or something. Load it. Oh, there we go. Root. Flag.txt. It's a little mangled, but we can see there's a root flag.txt. So what we're going to do instead of running this binary is we're going to go root flag.txt and we'll run it and we get the flag. Flag, go for your own request. So I think the way this challenge is supposed to work, this is probably supposed to be a setuid binary and the protections on root flag were incorrect. I think normally it should have only been readable by root, and I'm guessing the web process is not running as root. So you can use the Gopher protocol. So similar how we were using the file handler protocol or the file scheme, you can also use Gopher. And basically Gopher is a very clean protocol, and you can use basically treat it kind of like a netcat. Basically just going to send the contents of whatever's included to wherever you send it. And so you can kind of use it to tunnel locally and do a server-side request forgery, and you just have a lot of flexibility. You can specify like HTTP headers, all pretty cool. You can Google for it. It's a very common CTF challenge. But I'm guessing we're supposed to do that and then do, I think one of the routes, maybe the secret route required access from only localhost. So that's what you're supposed to do, but the flag didn't have correct permission, so we can download it. The next set of challenges were Ghibli Store. This was another set of web challenges. The first one says there's a hidden product and we need to find it. So if we go to the website, we can see there's a bunch of little products. If you view the network request, eventually you'll see there's a request being made to API products with query match in stock is equal to true. So we can send it to repeater and see if we can do it if it's not in stock. So we'll just put in a false right here. And we can see we get the flag. So flag simple match was all it needed. For the second challenge, we need to log in as admin. And there's a little login sort of thing here. The trick was to use the same API to leak out the admin password. So to do this, we can do a MongoDB injection. This $match is an aggregation operator in MongoDB. Instead of doing a match, we can do a $lookup. And so what this will do is this will join two different tables. It's kind of like a union in SQL. It's a little different in that you have to join on a specific field. One thing that's interesting, so let's go back to true, is the IDs. You see it's ID 1, 2, 3, 4. This is useful. Normally MongoDB IDs would be like an object ID, but since these are integers, we can actually do the join on those IDs. So we're going to have a user with ID 1 and a stock with ID 1. And since those fields are the same, we can join them together. How it looks is we're going to do $lookup. We're going to do from. We're just going to guess that the table is called users. Then we need a local field. We're going to use ID. So this is the field we're joining on. Then we need foreign field. Hopefully I spelled that correctly. ID. And then we need to specify what we want to join as. And we're just going to say user. So from the user table, join the ID field with the ID field and insert it into the results as a user. So we're going to hit send. And it worked. So we still get all the products, but like I said, we're joining this ID with the user ID, and user ID 1 happens to be the admin, and the password is super secret password leaked. So we'll copy that out, admin and password. admin password. There we go. And it says flag, you looked me up. Sweet. Next, it says something about we need to read files on disk. It's very similar to the last set of web challenges. So we can see there's this like database thing and you can export databases. If we click on this URL, we'll see that there's like some export API handler. So it's admin export file. We can see we're just specifying products.json. So let's send this to repeater and let's see if we have local file inclusion. So we're going to take this, and instead of doing products.json, we're just going to go up, oops, up, Etsy password. And we can see we get the contents. So we can leak contents from disk. From here, we need to figure out kind of where we are. We don't know what files to leak. So we could try kind of like guessing around. So we can do like app server.js and stuff. I think there's some headers for Express, so we know it's a Node.js app. But that doesn't work, so we can do the same. We can attempt to do the same thing we did for the last challenge. We can do proc self command line, but we only get back the first letter. I think I saw this at a different CTF challenge. I think Node.js will do like a stat call first, and I think procfs doesn't work well with the stats syscall. I think it returns like 0 or 1 or something. So then when it does a read, it's only allocating like a buffer of 1 or something like that. So this doesn't work. But that's okay. There's another very useful thing in procfs called current working directory. So we can do proc self current working directory index.js, and we get the results. You don't know that it's index.js, but if it's a Node.js app, it's going to be like index or server or app or something like that. So we can just try a couple of those. But there we go. We get the flag. It says, did you guess or took the proc route? So we definitely took the proc route. From there, it says something about a secret route, same as the last set of web challenges. So there's this routes thing. So we can try loading that. So we're going to go current work directory, routes, index.js. Cool. We can see there's something called secret flag. That looks very interesting. It's on secret controller. So let's find the secret controller. So it's secret controller. So it's not in routes. So controller, secret controller. We'll load that. We can see it's very similar to the same last challenge. It's going to execute this binary read last flag. Same, you can download this binary. You'll find out that it's loading a flag from root flag. And we get the flag. It says you binded your way in. I think this was also supposed to be a setuid binary challenge, but the permissions were wrong. I think the way that we were supposed to solve this, again, you can see on the secret flag request, it's only going to allow us if our web request is equal to localhost 127. So we need to be able to do a server-side request forgery to hit this endpoint. If we look at the import, so this was on admin controllers. So let's load that admin controller. There's a route for importing schema. This schema will parse the URL we give it, and it'll make the request for us. So I'm guessing that we were supposed to execute a server-side request forgery on the import schema call to leak the flag. This will then create a file on disk that we can then read with the flag contents. But since the permissions were wrong, we didn't have to do that. But otherwise, we would do the server-side request forgery. But fun. The next challenge is warm-up pwn. For this challenge, we're given a download binary and libc. And we're supposed to get shell on the remote system and cat out the flag. So this was actually a 32-bit binary, which you don't really see too often in CTFs. But if we look at the code, it's going to do some buffering, some more buffering. It's going to print out warm-up shell. It's actually going to give us the address of system. So we have our info leak. So we know where the libc system function exists. Then it's going to call this vuln function. Vuln function is going to define a buffer of 36 bytes. And then it's going to read in 256 bytes into that 36 buffer or byte buffer. So we have an obvious buffer overflow. And then from there, obviously we're going to jump to system and call bin shell. To see what the solution looks like, first thing we should do is make sure that there's no protections on the binary. So we can run check. It was file target, I think. Yeah. So we can see there's no stack canary. So when we do our buffer overflow, we don't have to know what that secret value on the stack is. NX is enabled, so we're not going to be writing shellcode directly to the stack. We're going to have to do some sort of jumping, and specifically we're going to do a ret to libc. And there's no PI, no position independent executable, so we don't have to know the addresses of the main elf, but we still need an address leak for libc because most likely ASLR is on. But thankfully they give us the leak to libc or to system, so we just need to do a buffer overflow and then do a ret to libc. To see what the solution looks like, this is pwn tools, so this is all generic stuff, just loading up the binary. They gave us libc, so we need to make sure we use it. You can link this version of libc to the binary using pwn-init. I don't think I do it. If you don't, I think it's probably going to use the local libc, which we can see. you can do LDD to see which dynamic libraries this binary is going to use. And we can see it's going to use the libc of my system. And so my system is probably using 235. I think I'm on Ubuntu 22. So this is the wrong libc. So if you tried to match like the offset of system, like I said, it's just using the wrong version. So what you can do is use a tool called pwninit while developing your exploit locally. So you'd say bin target, libc is the libc they give us. And what this will do is this will like kind of take that binary and patch in the correct version of libc and the correct linker, and it also unstrips libc, so you get debug symbols. It's all amazing. But that way you know that the binary and the libc that you're using locally are the same ones on remote. So highly recommend doing this, even though I was kind of lazy and I skipped it the first time. But eventually that'll run. I'm just going to cancel it. Cool. We're going to run it locally first. So we're going to receive, actually, let's just run it. So like I said, it's going to tell us the address of system, and we can see it is at this address. So we need to copy that out. And then we have our buffer overflow. And so you can see we get a segfault. So we're going to receive until that system at, we're going to grab that line. It's hexadecimal. So we're going to parse it, grab the system. We're going to calculate the base of libc. So it's just whatever value we got minus whatever the offset of system is in libc. By default, it says libc.address is 0. So you can just subtract them to get the correct address. From there, we need to calculate the offset of where the buffer overflow starts. It said that it defined a buffer of 36 bytes, so maybe it's the 36th byte is where, you know, the frame pointer and the return address are. But an easy way to calculate this without having to do guesswork or checking is you can attach GDB. After it asks for input, we're going to send a pwn cyclic of OX 100 bytes. So it's going to look like AAA, BAA, CAA, DAA, blah, blah, blah. And we're going to use this to calculate offsets. And then we enter in an interactive. So the reason we do this is Python 3, solve.py. Oops, too far. Let me rerun. So on the left, I have the program. On the right, we have pwndebug, which is GDB with an extension. So I'm jumping all the way back to the vulnerable function. So we finished reading in this giant input. We're back in the vulnerable function. I'm going to step forward a couple. So we just did some add ESP, some nop, some move, some leave, and now we're about to return. So on the return, it's going to pop a value off the stack and jump and start executing there. Normally it would go back to the main function, but since we did a buffer overflow, it's now clobbered. The stack is, you know, whatever it is, and it is going to return to LAAA. So, you know, obviously this is not a real address, but we now know the offset of where we need to put our return address. So instead of putting LAA here, we need to put system. After this, we also want to put the arguments, and we're going to put that right afterwards. And the arguments we want is the string bin shell. So somewhere in libc exists the string bin shell. So we can do search bin shell. We can see it exists here within libc. So we just need to find this address and pass it as an argument. So eventually it's going to call system bin shell, and you know we can do whatever we want from that point. So like I said, LAA was the offset that we needed. So there's a very cool tool in pwntools called pwnflat. We're just going to pass in LAA. Really under the hood, this is doing pwn cyclic find LAA, and this will return like 36 or something like that. But we're saying at the 36th offset, or whatever the LAA offset is, I want you to pass system, the address of system, which we already calculated or it was given to us, and then pass in the string bin shell. So it's going to take our libc, it's going to search for the string bin shell, and then just return the first instance of it. That's what the next is, and I just passed it twice. Cool. I think normally people like to pass an exit here so things exit correctly, but it doesn't really matter. Cool, yeah. So we can try running it remotely. Pwn, warm up site, no more GDB. Yep, everything's good. Python 3, solve.py. And we type in ls and we can see we have shell. So now we can cut out the flag and we get it. Flag ret to simple overflow. So fun. The next two challenges were called Duck Hunter. These were programming challenges. So we're given a netcat port. If we connect to it, prints out a duck. It says select the level. We're doing level 1. And it says, okay, how to play. Receive a 25 grid, locate the x. So we can see there's an x here. On the grid, return the xy coordinates of the x. It starts at 0 at the bottom left, and repeat this 100 times. So just programming. We just need to download this, figure out this coordinate, and return it. And we have to do it 100 times, and then we get the flag. My solve script looked like this. I'm using pwntools again. Just usually it's used for binary exploitation, but you can use it for anything. And it just has a lot of good buffering capabilities. So I'm going to import pwn. I'm going to set the log level to debug so I can see all the input and output. We're going to connect. So it's going to ask us for the selection. I'm going to say I'm doing level 1. And then I receive until this line, repeat 100 times to get the flag. This is the box character. I just copied it out like this, put it here, and then encode it as UTF-8. So while true, so really this should be for I in range 100 or something, for all 25 lines, grab the line. I just print out some debug information for the line, count out how many boxes there are. If there's no X, there should be 25 boxes. If there is an X, there's then only 24 boxes. So I'm just printing out debug information. If the line has 24, this means that there is an X on that line, so we know the Y coordinate. So then we're going to calculate the X coordinate. I just do a split on the X and I count how many boxes are to the left. And from those two things, you know the coordinate of where it is, and we send it back. Yeah, we repeat that 100 times and we get the flag. So Python 3, this was duck 1. And we're off. Cool, eventually it's done, and it says flag, shoot them ducks. So fun. Then there was Duck Hunter 2. So we can go into the second level. This time it says receive 2025 grid, receive which duck to locate. Starting from the top left, there will be a single number, locate that duck, blah, blah, blah. So it's similar to the last one, except we want the fourth duck. And so this is duck 1, 2, 3, 4. So I think this is the duck we want. I could be off by one. So we want to return these coordinates. So similar to the same one, just a little bit different. I did a slightly different strategy this time, so all the same import pwn stuff. This time what I do is I load in every single line and then I join them together. And so I just have one giant line that has all of them. And then from there, I'm just going to iterate through. Every time I see an X, I increment my internal counter. So right now the counter would be 0. It starts at 0 and we're trying to go to 4. So I'm just going through this giant string. But once I hit the fourth one, I know where we are. And since it's one giant string, you can calculate the X, Y coordinates by doing X mod 25 and Y divided by 25. Technically it's reversed because this is 0 and this is 24 up here. So you have to do this 24 minus I divided by 25. Hopefully that makes sense, but yeah, and that was it. Python 3, solve duck 2. And there we go, we get the flag duck sniper. So fun. The next challenges, or the next two challenges, were shape identifier. For this, we're given a netcat port. It was another programming challenge. So if we connect, it says shape identifier, we're level 1, we'll click it. So it says receive this base64 string, it's an image. Find the shape in the image and return that shape. So it's either a square, triangle, circle, oval, hexagon, and do it 100 times, you get the flag. So you can take this, you do a base64. Actually, we'll just do it. So we copied it, we'll echo this, then we'll do base64, decode, and we'll do test.png. Cool. Then we can open it up, test.png, and we can see we have this shape. So this shape happened to be a square. There are a bunch of different shapes. So here's an oval, another square, a test, a triangle, a hexagon, circle. These are all the shapes. So this challenge could have been very hard if the shape sizes were like moved around a little bit, but thankfully the shapes are always the same. So a circle will always have this shape, I guess. Just the colors will be different. So we know what the size and the dimensions are. It's just the colors are different. Thankfully, that makes this much simpler than it could have been. Like if the shape had been moved around, that would have been very difficult. But what we can do is, since we know like the dimensions of the shape, what we're going to do is we're going to connect. We're going to download the PNG file. We're going to save it. We're going to open it up just using, you can use any image library. I just use PIL, Python image library, and we're going to grab out the pixels. And what I'm going to do is there's a background color and a shape color. I just call it the first pixel and a middle pixel. And so these are the two, it's either one of those colors. And then from there, I convert it just to a giant string, I guess, of zeros and ones. So the background color is 0, I think, and the shape color is a1. And I'm going to do that for the square, the triangle, the circle, the oval, the hexagon, and the octagon. So I downloaded all of these images and I saved them as those files. As we already saw, I got octagon and oval. Since I know what these are the correct shapes, I guess, I'm going to download the kind of like the base reference. And then for all of these other rounds, all 100 rounds, I'm going to download a new shape, convert it to zeros and ones, and I'm going to see if it matches the known zeros and ones for one of these shapes. And yeah, that was my solution. Like I said, I have all of these. I just have a function called getShapeMapping. Like I said, I'm using this Python image library. I get the first color, I get the color from some pixel in the middle, and then I iterate through all 100 by 100 pixels. If it matches the background color, I append a 0 into this giant array. If not, I append a 1. And then from there, we know the shape of all the shapes. And then from there, like I said, for 100 rounds, I'm just going to download the new file. I call it flag.png. I get the shape of that one I don't know. I compare against all of my known shapes, and if it matches one of those known shapes, I print out the shape, and that's it. So Python 3, solve.py, and we iterate 100 times. Cool, and then we're done, and it says flag, pretty shapes, go burr. The second round of this was a little bit more difficult, but still not as difficult as it could have been. Thankfully, the shapes were still predictable. So for this challenge, let me just netcat actually, and I'll read the rules. So we get a bigger image, as you can see. It says there's going to be both a shape and a number in the image, which we can see here. And what we needed to do is we're going to return an integer and the shape. And the integer will be the multiplication of one of the colors and the color of the background and the foreground, and specifically just one, either the R, G, or B, depending on the number. So for this case, the number 1, so we're going to take the R out of the RGB, and we're going to multiply the redness of this with the redness of this, and that'll be our integer, and then we also have to say what shape it is, and it's a hexagon. Again, this challenge could have been so much more difficult if these numbers and stuff moved around. Thankfully, they don't. The numbers are always in the same place, and the numbers is equal to 1, or either a 1, 2, or 3. So we have a 1, a 2, and a 3. And so you can see the numbers always in the same place. And then we have the same shapes. The shapes are always in the same place, and it's the same shapes that are up here, making it much easier. We can see there's also no overlap, which makes things much easier. We can divide like a line right in the middle, and we don't have to worry about anything. And yeah, so because of that, we can do pretty much the same solution we did last time. We're just going to look at like the shape of the shapes to determine the shape, and the shape of the number to determine the number. So like I said, we have these 3 files that I already downloaded, 1, 2, and 3, that have our reference numbers. So we're going to calculate the shape of these numbers. Sorry, let me back up. For each of these images, I'm going to divide the image in half. When I take it, I either want the shape or the number. And so for the numbers, I'm going to divide it in half, and I'm going to record the shape of just this bottom half. And so then I keep that as my reference 3, my reference 2, just the bottom half, and my reference 1. And again, using the same thing as last time, I know what the background image is, and I know what the color of the shape or the number is. And then I just construct that long array of zeros and ones, and I just do, does it match or does it not match? And yeah, one thing that's a little bit different about this is you can see there's a little bit of shadow here. And because there's a little bit of shadow, it makes it just a little bit more difficult. We can't, it's not all either this color or this color. There's like some blended colors. For that, because of that, they mostly have the same shape. Basically, I say it's either the background color or it's a non-background color. So I include the blur as just red, I guess. And I match that shape. I think every once in a while it's like off by like a single pixel or something like that. And so I just say like the difference between the guess array and the reference array is like less than 5 or something. There can be like 5 differences. So 5 little pixels can be off, but otherwise they have to be the same. And yeah, that was pretty much it. Can't load. So this is the solution, same sort of stuff. I'm using Pwn tools. I'm going to get the shape mappings. So I call it that giant array, I just call it mapping. I'm going to load it up. So I want both the top and the bottom are different. The top has the shape, the bottom has the number. I'm going to go through. First thing I do is I grab every single pixel and I see which pixel color is most popular. The most popular pixel color should be the background, and the second most popular pixel color will be the actual like shape color. So this is red, just because there are a couple of different colors in here. It's not just blue and red now, or teal, I guess. There's teal, red, and then like the shaded colors. So just a simple way to grab the 2 primary colors is they're the 2 most popular pixel colors. So I just generate a histogram of these, and then I sort the histogram, and I grab out the 2 most popular colors, which is color 0 and color 1. I print out the third one just to make sure that there's no like, not race condition, but maybe there's a lot of shading or something, but it never ends up being the case. So I know the background color and the shape color, and then I do the same thing as last time. I'm going to grab out the shapes from just zeros and ones, same for the top shape and the number. I do it for both the top and the bottom, because the top is always a shape and the bottom is always a number, and I return that. Like I said, this time, because of the shading, it's not going to be the exact matches of zeros and ones. So I have this difference function. It's going to calculate the difference between those 2 long arrays, and then I just go through. I'm going to save the new flag.png. I'm going to try to calculate the shape. If the shape between my reference image and the guess is less than 5 differences, so less than 5 shade differences, we know what the shape is. Then I do the same for the numbers. As long as it has a difference of less than 5, we're good. And from there, we just do what the program says. It says take out the colors, the RGBs based off of the number index and multiply them together and then return that. So I take color 1, which is the color of the background, I think, color 2, the color of the shape. I multiply based off of the number that was in the image, just as what the problem statement says, and I return it. And that was it. So Python 3, solve 2, shapes 2. And we let it run. So this one's a little bit slower, but... And there we go. Shapes and math go burr. So fun. The next challenge is Pwn Hippity Hoppity. We're given a netcat port and a download file. As far as I know, this challenge wasn't solvable remotely. It was very easy to solve locally, just remote wasn't working. I'm guessing that they probably recompiled it remotely, so the line numbers don't quite match up. I don't know of anyone that solved it. I asked a couple times in Discord. If you did solve it remotely, I'd love to hear how. Maybe I'm doing something wrong, but I'm guessing it's just the remote binary is a little bit different. For this challenge, so there's the main function. It's going to do this init. It's going to put, then it's going to do an unbounded gets. So we can see that they're defining a buffer of 10 bytes. It's going to do gets on it and then a return. In this init function, it's a little strange, but it's going to do some buffering, which is very standard. Then it's going to call hoppity and hippity and super secure checker. In hoppity, if this value is equal to 1, it's going to cat out the flag for us. And in hippity, it's going to set it to 1. And it also sets it to 1 out here. So ideally, we're going to be doing some sort of like ROP, I guess, but we're just really just jumping back to this function. You can ignore all the super secure stuff and just jump straight to the system call. So right here, this load effective address is going to load the string cat flag. So instead of we don't even have to worry about this compare. We're just going to jump straight to this line. So 401.705. So we can copy this line out. Let's jump into an Ubuntu box. We also don't need libc. This was statically compiled. So if you look, there's just like a whole bunch of functions. That's just because libc was included. But we also don't need libc because system already exists in the global offset table and it's right there. Cool. So yeah, that was the challenge pretty much. We just need to jump to that target address, which was 401.705. We copied it over. One other thing we should do is check the protections. So we can do checksec file. This is called chal. Yeah, chal. We can see there's no position independent executable. So our 401 target address or whatever is going to work fine. There is a canary, which is interesting. But if we look, the canary is not being used within our main function. So we don't have to worry about it. Go back, and go back. Normally if there's a canary, it'll do some like if fsox18 or something like that is equal to some stack value, then go to stack check fail function. We don't see that here. So the canary is not being used within this particular function. So we don't have to worry about it. And we don't care about NX. We're not going to be writing shellcode because there's already a win function defined. So we just need to jump to that. And that's pretty much it. To see the solve script, nice and simple. All standard Pwn tool stuff. We're going to load the library, or sorry, start the process. I just do it locally. So normally you can do a Pwn cyclic like we did for the last Pwn challenge, and you can calculate the offset of where you're supposed to put the return address so it gets popped into RIP. But we can just kind of guess and cheese it. We know that the buffer size was 10, which is a little bit strange. So I kind of just guessed this. I think maybe I looked in GDB and I saw it was like I needed to shift it by 2 bytes or something like that. But you can shift it by 2 bytes. And then I think originally I was just doing Pwn 64 target and you multiply it by like 10 times. This is just being lazy. Eventually, you know, like at some point you're going to overwrite the RIP that's on the stack. And so when it does that return, it's going to jump. We don't know what offset it is, but if we just spam the target onto the stack, we know eventually it's going to jump to what we want. So you can do this. There's one other issue that I think I ran into, which is why I have this return in here. So libc, modern versions of libc require stack alignment. And this is because, actually, let's just run it. We'll see what happens. I'll show what it looks like times 10. We also need a pwn.gdb.attach p running locally, tmux python 3 solve. So we're finishing. So I clobbered the return address on the stack. And so we're in the main function right now. So we're going to do a single step. Now we're doing leave. Now we're doing ret. We return to the hoppity function, which has that load that string and then call system. So we're loading the string at RIP, whatever. So this is the cat flag, I think. Then we're moving that into RDI, and now we're going to call system on cat.flag. So if I do a next, I think, oh, it works anyway. So we don't even worry about the return address. But we can see it actually prints it out a whole bunch of times. That's because we just spammed the target address onto the stack. So it's going to call the system cat flag like, 4 or 5 times because we just spammed it. I think I was doing the return address in case the remote was different, but we don't have to worry about that. Sometimes, anyways, there is stack alignment, and what that happens is modern versions of libc use some instructions that require things to be like 16-byte aligned, and there's just certain assembly instructions that just require like the stack variable to end in a 0, for example. And when you do that, you can just put in an extra return statement. So this is the address of just some random ret. And so what that'll do is that'll just push the stack down by 8 bytes. And so that way everything aligns correctly, but we didn't even need it. Like I said, I tried running this on remote. I tried a whole bunch of different things. Like maybe it was this. I tried jumping to different targets. I tried jumping back to the start of main to get it to print again. Like I said, I think it's just they probably recompiled the binary on the remote system, and just it's different than the binary that was provided to us. I also think that way because when I jump to different targets, different addresses, sometimes I get illegal instructions and sometimes I get segfaults. So I know that the jump is working itself. It's just jumping to different stuff. And if I specifically jump to this target, I get legal instruction, which probably means that it's jumping in between like an invalid offset into assembly. So yeah, again, if someone did solve it, I'd love to let it know. I think for the last 5 minutes of the CTF, I actually was doing something like for target in range, starting like like this minus 100 and then plus 100. I tried to kind of fuzz it and go through, but it wasn't working. But I imagine that since I was getting invalid instruction and segfaults, you might be able to kind of fuzz it, but it might take many thousands of requests, and I didn't want to be too mean to the challenge infrastructure, but yeah. And the last challenge is Baby ROP. We're given a netcat port and a download file, and it says we need to get shell. It says libc is attached, but it's not. But technically we don't even need libc, we can calculate it, which is what I ended up doing. Eventually later in the CTF, they told us that we could use the libc from the previous challenge, but I'm going to show you how you can calculate libc, which is sometimes a fun challenge. And yeah, let's get started. So very similar to the previous challenges, there's some main function. It's just going to print some stuff out. It's going to call this vulnerable function, and we have a trivial buffer overflow. So from this buffer overflow, we're supposed to get shell. We can see there's no obvious jump targets. So normally we're kind of doing a ret to win. Here, there's nothing to jump to. So we need to be a little bit more clever. We can check the protections. So let's do checksack, file, target. We can see there's no pi, so that's good. So we don't have to get a main elf leak. We can jump right back to the main function if we want. There's no canary, so we're doing a buffer overflow. NX is enabled, so we're not going to be writing shellcode to the stack. And that's pretty much it. So to solve it, like I said, at first I didn't think there was libc. And so I went to calculate libc. And the way to do this is we're going to do a buffer overflow, same as we've done the previous times. You can calculate the offset, again, doing pwn cyclic like we've done the previous times. You just do KAA, or do the pwn cyclic, open it up in GDB, see what return value it's going to jump to. In this case, it was KAA. So we know what the offset is. From here, we're going to start ROPing. We're going to use pwn tools to make our ROP payloads for us because it's absolutely amazing. The first ROP payload will just be a return. So you can just like load in the gadget or return address. Let's just do that. We're going to do ret. So here is some ret address, 401. Let's do ret adder is equal to OX, this value. So instead of finding a ret gadget, we'll just put one in manually, ret adder. And the only reason I have these is just because I think there was some weird stack alignment issue or something, so I just place them in there. So we're going to return, which does nothing. Then we're going to have our ROP payload call printf with the address of the global offset table entry for printf. So if you're not familiar with global offset table entries, basically it's just a way to kind of link different functions between libraries. So we have our like main binary, and it's going to use the libc that is on your system. So you already have a libc file somewhere on your machine. Was it called target? We can see we have libc right here. But when the binary is being loaded, it doesn't know libc is going to be loaded into the process space of the binary, but it doesn't know where those addresses are. Like it wants to call the system or printf or whatever, but it doesn't know where it is. So as part of the linker loader process, it's going to be placing those values into the global offset table. Technically, it's like forgetting the word, but it'll be loaded when it's first needed. I think there's a word for that. Not just in time, but yeah, basically when it's needed, it'll be calculated. And from there, those addresses will exist within a known memory address within the main binary. To see what this looks like, let's do GDB target. Let's run it. Okay, so we're in Pwn debug. We can see everything's cool. I'm going to type in got for a global offset table. So at this address, since it already called printf, it loaded and calculated the value of the printf call within libc and put it here. So the printf currently exists at 0xFFFF7D6F, and that address is stored right here. So like we can take it, examine 20G at this address. We can see printf is at this address. If we do vmmap to see where everything is in the process, we can see we have our known addresses. This is like the main elf, baby ROP target. And we can see libc is loaded here. I think I have ASLR off, which is why the addresses are so nice. But we can see libc is here, and as part of that linker loader process, it was able to calculate those addresses and put them in the global offset table. Since we know the addresses of those global offset table entries, what we're going to do is we're going to construct a ROP payload that prints those values out. Libc, so it is going to be random within process space. But if you notice, even with ASLR, the last three nibbles, so the last three 4-bit chunks, they're always 0. And so you can actually leak a bunch of different global offset table entries or libc functions, and just based off of the last three nibbles, you can actually calculate the libc version. So to see what this looks like, and we need the libc version because we're going to be returning to libc eventually, and we need to know what version of libc is so we can calculate the relative offset to the system call and stuff like that. So I'm constructing a ROP payload. We can ignore, we're just doing this for stack alignment. I think I discussed in a previous challenge. We're going to printf the address of the global offset table entry for printf. So let's just run this real quick, Python 3, solve.py. We got our leak here. So this is the address of printf. So again, this is all random, but this E40 is not random. So what we're going to do is we're going to take this to a libc database right here. So the symbol for printf is at this address. Cool. We then need to leak another global offset table entry. So we see what else they have. They also have fgets. So sounds good to me. So we're going to go here. Instead of linking printf, let's leak fgets. So let's rerun it, and we're running this on remote. So we're leaking the remote values. So we got the next address, and it is this one. So we're going to do fgets, this address. And you could do more. I think there was also set vbuff, but 2 is usually enough. So we're going to find, and this libc database will calculate the libc version for us, and we can even download it. So they're using libc 227 Ubuntu. This is the libc version used on a different challenge, so if we had waited in Discord, they would have told us that we can just use it and you don't have to do this, but it's just good to know how to do this stuff. Anyways, now that we know the libc version, we can do opt pwninit again. So we can link the libc that the remote system is using into our local binary, so it's using the correct version when we develop our exploits, and so we don't have to do any fiddling, trying to get things work locally and remotely, which is very frustrating. I guess I kind of skipped over this, but this is how we send the payload. I think I discussed this in a previous challenge. One thing that's a little bit differently is RBP is on the stack, and we don't want to clobber RBP because we're going to be making repeated calls. So we should set RBP to a writable value. And so a writable value you can use is elf.bss, which is just a readable writable section, plus OX500, so it can go up and down a little bit. And that way our stack values, while they're not going to be the OX7 FFF values that they're normally, they're at least readable and writable, and we can just use that as our stack moving forward. So we send it over, that payload, to printf the value. We just grab it, so it's going to print out those 6 bytes from our leak. We can kind of see it here. So here it is printing out fgets, I guess. So it prints out 6 bytes. We need to add 2 null bytes to the start. And then we can do a pwn u64, so unpack the 64-bit integer into our leak. And now we know what the leak is. Let me move this back to printf. And it'll print out that value for us. So now we can calculate the base of libc, so it is the leak minus the offset to printf within libc. And we also have the libc version, thankfully. Where do I go? Oh yeah, here it is. Oops, going blind. Libc, we're loading it locally. Libc, so we know what the offsets are. Once we know where libc is, we know where the system call is, and we know where the bin shell string is within libc, or we can calculate those. We've done this for a previous challenge, so we're going to construct a second ROP payload. So we're going to do ROP, find a return address just for stack alignment reasons, and then we're going to say ROP, I want you to call system with and set RDI equal to bin shell. And so it's going to find the bin shell string within libc. It's going to set up the registers correctly so that we can make the system call, and then we send it. So we say, we give it another good RBP that's readable and writable just in case, and we send off our chain and we wait. So we can run this, Python 3, solve.py. It takes a second to load libc. Then it sends the second payload. We can do an ls, and we can see we have shell. So cat out the flag, and flag ropped my way to system. So fun. Cool. And that was all the challenges. So thanks to Sans for hosting, and I will see you all at the next CTF. Cheers.